I just saw Brandon too.
Nice. Alright, section 9.5, binomial theorem. We're taping just in case someone doesn't make it in. What did I do yesterday? I cheated. Kind of. As you guys are writing. How would you have had to do this in the olden days? Foil. Wait, but it's cubed. How do you foil if it's a cube? Just like we normally do multiplication, right? Multiply the first two, and then when you have an answer, multiply it by the third one. So then we would have had to do a squared plus 2ab plus b squared, which some of us can, most of us probably, can kind of do a squared mental math as long as you don't kill any photocopy. But then we would have had to do polynomial multiplication. P.S. By the way, what I'm doing is the olden days how to solve. You would have had to say, oh yay, he distributes to everybody. Oh yay, he distributes to everybody. Oh yay, he distributes to everybody. Ew. But you would have ended up with a cubed. Let's see. We would have ended up with a cubed plus a squared b plus 2a squared b plus 2ab squared plus ab squared plus b cubed. Which then you could have combined some like terms. You would have ended up with a cubed plus 3a squared b plus 3a squared b plus b. So how did I get there so fast yesterday? I worked it out before, memorized it, just look smart. No. Wish I had time to prepare that much. But
Am I wrong, or is this a triangle?
I used a triangle. Whose triangle?
Pascal's.
Maybe it wasn't his, maybe it was his followers. But either way, Pascal's triangle. Now, hold on. What's this super complicated thing down below? What's going on with that binomial theorem? How does that relate? Can anybody tell us something that relates to what's up above? Yeah, kind of the n. Because n is the power that what? That the binomial is being raised to. Wait, binomials? What are all these guys? Oh, they're binomials. And what are they being raised to? Higher powers, right? So you can think of, okay, who's n? I don't know, maybe, oh, sorry, I flipped him. Who's n? I don't know, maybe he's 1, maybe he's 2, maybe he's, well, we don't know who he is, but whoever he is. Maybe what I did above, and maybe what Pascal's triangle shows is going to help us with this binomial theorem, which is the most important part of section 9.5. Can I zoom in on binomial theorem yet? If you guys to write it, is that okay? X plus y to the n. How to expand him. There are multiple ways of thinking about it. And Pascal's theorem does, or Pascal's triangle I should say, does relate, and we're going to see how on the next page. But for right now, using strictly mathematical formulas, you can, without forming a triangle and needing to follow certain steps to jumpity jump jump recursively to the right spot, you can use this thingamabob called NCR. Does anybody remember his actual name? Combination. We're building up to probability. Combination. Permutation? Oh yeah, that was a thing. combination. C is for combination. And to be honest, he is usually used in probability, but he can be applied in this kind of example. Because the combination actually ends up being the proper number in the proper place when we are expanding binomials in Pascal's triangle. And we'll see the correlation on the next page. But for right now, do you guys see certain trends, like, for instance, as you look at this formula that you wrote out, n is going to be the power that you're raising to, right? What do you notice up above about how the a's start out for raising to the first power, second power, third power, fourth power? How do the a's start out? To that highest power, right? Okay. Where do, see how the n shows up with x at the beginning? Doesn't the n show up with y at the end? What do you see the common trend of b's on the latter end, or on the right-hand side of each of these expressions? To the first power, to the second power, to the third power, to the fourth power, right? So what's going on in between all that stuff? What does the a have to do in its powers? Count down. If a is to the first power, he's gone in the next. If a is to the second power, now he's to the first power in the next term. Then he's to the 0 power, he's gone in the third term. If a is cubed, now he's to the second power, now he's to the first power, and now he's gone. If a is to the fourth, now he's to the third power, now he's to the second power, now he's to the first power, and now he's gone. But as a is counting down, what's b doing? He's counting up. B is non-existent in the first, and there he is. B is non-existent, then he's to the first power, then he counts up to the second. B is non-existent, first power, second power, third power. B is non-existent, first power, second power, third power, fourth power. So what happens to the first terms? Start at the highest and count down. How can we see that in the formula? X to the n, and then what's going on with x? He's counting down. Subtracting one, then subtracting another, subtracting another, subtracting another, until finally there's only one x left, and then poof, he's gone. What are the y's doing, or the second terms doing? They start non-existent, and then all of a sudden, there they are, and they are counting up. They are counting up, until finally they've reached their climax at the other end. All those are patterns that theoretically you guys have seen before, if you've seen binomial theorem before. But the dealio is we're not just going to say, hey, expand this binomial to a high power and show off how you can do it so quickly. There are going to be some other questions involved, and once again, we're just kind of leading up to probability. So, a few other important things to talk about. This is the first time this year that we've seen the combination formula, so he's pretty stinking important, this guy right here. He lets us jump to a specific place without having to do Pascal's triangle, even though Pascal's triangle is really cool for the first few powers, the first few rows. Sorry, air fade. Even though Pascal's triangle is pretty cool for the first power, second power, third power, fourth power, past that, it might get a little annoying. And it might be easier to have a formula just to plug into and jump to a spot. So binomial theorem number 1, we have the formula for a combination number 2, and then we have this new little symbol for NCR. Another way of writing NCR is to write N and R in these little parentheses. It does not mean a fraction, it does not mean divide, it literally means NCR, same thing. Same thing. Okay, but hold on. When I did all that stuff yesterday, even today, a lot of you guys are like, hey, wasn't that a triangle? And the answer is yes, but before we get to the triangle, let's play around with that NCR thing just for a little bit. Let's play around with that NCR thing just for a little bit. So then, working on examples. From the page before, help me out real quick just so we can refer to it. What's the formula for NCR?
factorial divided by minus r factorial times r.
Good thing we kind of practiced factorials earlier in chapter 9, huh? Okay. N factorial over n minus r factorial, r factorial. So, just in case you need to label stuff, if 8 is on the left-hand side, that means n is 8, and if 2 is on the right-hand side, that means r is 2, right? So how do we plug and shove?
8 factorial over 8 minus 2 factorial.
How do we simplify by hand? Oh, struggle. Don't worry, calculator has its place. We'll learn how to use them, but
Write them out.
write them out. So I have 8 factorial over 6 factorial, 2 factorial. Question, how do I know that's 28? Wait, what? Magic? Quick mental math? Yep. I knew 8 factorial, I knew 6 factorial, I knew 2 factorial, tons of multiplication and division. False. Not even close. Nope, that wasn't it. That's hard. What can I reduce? What
The
can I do?
6 and the 8.
Nope, don't do that. That's
You can
illegal.
reduce the 2.
Good idea, but no.
Using 2 and 1.
Yeah, I can say that 2 factorial is 2 times 1. I could say 6 is 6 times 5 times 4 times 3 times 2 times 1, but I'm not going to. How come? So, can't I take 8 down until he meets 6? Isn't that spiffy?
Oh.
I can take 8 down until he meets 6. Because it'd be 6, 5, 4, 3, 2, 1, but I have a 6, 5, 4, 3, 2, 1 in the denominator. Can I say, sweet, those reduce. And then,
56 divided by 2.
see the 2 and the 8? Can't those reduce?
Yeah.
To be 1 and 4? That's what I did. What's 4 times 7? Dun, 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 dun.
Fun.
Not bad, right? Not bad if you do it that way. If you do 8 times 7 times 6 times 5 times 4, that'd be fun. I know 5 factorial is 120, but then times 6 is 720, times 7 is, let's not do that. Let's see if we can reduce stuff. You guys gonna play with factorials and letter B? Let's see what you got. Let's see what you got by hand. Let's see what you got by hand. If a few of you are trying to grasp at what's combinations in terms of probability, 10 total items, choosing 3, and the order does not matter. But don't worry, we're not there yet. That's not the point of this section. We're introducing a different application of this combination. And just in case a few of you guys are still stuck, remember this notation relates to 10C3. Just in case the notation tricks you. 10 choose 3. 10C3 is what that parenthesis notation is showing. Can I have fun with factorials now? Do you want me to cover that?
Yeah.
120, right?
120.
Just a few of you want to know how we got there without a calculator. Plugged into our formula. What'd you guys do? Talk it out. Luca, do you want question first or do you want solution?
No, but it's for C.
Okay, hold on. What'd you guys do that got 120?
8 plus 7, 7, 7, 5, 7. It's just 7, which means 20 over 6.
You can take out the 3 from what I did. I did 3 and 9 and 2 and 8. But there are multiple ways. You could have done the 2 with the 10. You could have done 6 and 8 reduced to be 4 and 3, and then 3 and 9 is 1 and anyway. Lots of ways. You could end up with, right, 1 and 3. 1 and 4. 3 and 4 is 12, 12 and 10 is 1. Okay. Ooh, math.
Yeah.
Go over to probability, and it's number 4. Math, go over to the end menu, so go right 1, 2, 3.
Oh, I see.
And then number 4.
It looks so weird in mine.
But then, you'd have to do factorials like 3 different times in your calculator. That would take forever to write in, blah, blah, blah. It's more fun to do the math. Sometimes.
Dot in the middle. Probably.
Okay, hold on. Someone had a question on C already because they were trying to be spiffy and go ahead. Good job. But, how do I solve? Formula says 7 factorial over. Can we just jump to subtract 7 and 0? 7 factorial, 0 factorial.
What about the 0?
Undefined! Wait.
No.
0 factorial equals 1.
Oh.
0 factorial is defined to equal 1. And then 7 over 7.
Solution.
If 0 factorial wasn't 1, we'd be in trouble. But since 0 factorial is defined to be 1, we say, oh, 7 factorial over 7 factorial is 1. And similar on the next one, 8 choose 8 or 8C8 as the notation shows would be 8 over 8 minus 8 is 0 times 8 factorial. 0 factorial once again is just 1, so 8 over 8. I apologize, 8 factorial over 8 factorial is 1. If you want to think about it in terms of probability that we're not supposed to be going into yet. If 7 is how many objects you have, and 0 is how many you're choosing, and this is how many ways you can choose where order does not matter. 7 choose 0, well there's only one way to not choose any of them. 8 choose 8, well there's only one way to choose all 8 of them, you'll get all 8. Once again, when order is not important. Now just a few of you snazzy ones are like, hey, not only is there a factorial button in my calculator, but there's also a
NCR.
Did you see it if you went to go find the calculator? Sorry, the factorial. What do we do with NCR? Well, here's the problem. You have to tell them a number before, like for instance, what did we do, 10? Oh, now it's gone. You have to tell it the N before, and then the NCR, and then the R after. Don't worry, it's good to know how to use your calculator, but you gotta know how to do it by hand also. You can double check and say, oh hey, 120 was right. Anyway, cool beans. This is a special, not just with factorials, I'm learning how to use them, but a special NCR, that's his own little special guy we're learning how to solve for him. Now kiddos, that's all well and good. But how on earth does this apply to that whole binomial multiplication thing I was doing? Yeah, going back to that formula, they're saying whatever coefficient is in front of a particular term, and if we want to define it, we could technically say that this is our binomial coefficient. This, x of n minus r, x to the power of n minus r, is the n minus r power of x, and then the r power of y. Now, don't stress too much about this. I'm preparing you for harder things to come.
That looks like the denominator. But in factorial.
Yeah, the n minus r, right?
Yeah.
And then you have the r.
Yeah.
There's a reason for that.
Mhm.
Okay. Let's go talk about Pascal's for a second. We've already done one page of examples, and this is going to be our second page of notes, and it's all about the triangle. We have one more page of notes after this, and then it's, okay, how do we use all this stuff? If I was to ask you guys to do, let's see, where do I want to start? each of these referring to? Yeah, NCRs, right? Isn't that what this notation is showing? If I was to have you solve each of these, hold on. If I was to have you solve each of these and put them in a triangular pattern, what would you find?
1, 1, 1, 1, 2, 1.
Because if you were to do 0 factorial all over 0 factorial times 0 factorial, that's just 1, right? If I was to have you do 1 factorial all over 1 factorial, 0 factorial, that's 1. If I was to have you do 1 factorial over 0 factorial, 1 factorial, that's 1. If I was to have you to do 2 factorial all over 2 minus 0, 2 factorial, 0 factorial, that's 1. 2 factorial over 1 factorial times 1 factorial, that'd be 2. 2 factorial over 0 factorial, 2 factorial, that's going to be 1. If I was to have you keep doing each of these, all the different little baby combinations, you would end up with a 1 and a 1 and a 1 and a 1 and a 2 and a 1 and a 1 and a 3 and a 3 and a 1. Now, this is Pascal, so we will talk about the pattern. Give me just 1 second. However, in context of what we've been seeing, where our little notation, N and R, corresponds to the coefficient of a certain term of a binomial expansion, aka N and R, would show up in x to the n minus r and y to the r, or if you think about it in terms of what I showed, a to the n minus r and b to the r. If n and r were 0, how does this apply? That would be 0, right? And that would be 0. Well, wait, hold on. This is going back to some sort of term in the expansion of x plus y to the n. Question, what is n in this very first one, 0, 0? 0. The power is 0. Off to the side, we'll write that. The power is 0, and there are 0 terms because anything to the 0 power is 1. There's nothing else. The next one, n would be 1, and there would be 2 different terms in the answer. N would be 1, which means I'd have x plus y to the first power. And kiddos, when I expand that, aren't I going to have 1x plus 1y? 2 different terms. And the third one, I'm going to have x plus y squared, because now n is 2 in my expansion. And how many terms am I going to end up having? That's indicated by the r. I'm going to have a 0th term, a first term, and a second term as far as powers of the second. And we know that we'd end up with x squared plus 2xy plus y squared, 3 different terms with 3 different coefficients. And we can keep this pattern going. But what do you guys also notice about a way of remembering? If you're just using the triangle, a way of remembering which power you're raising it to. What can we look to? Shouldn't these all line up? Shouldn't the ends be the same? Now how's it going to translate to Pascal's down here? Well, the top one is going to be, let's go ahead and just do a little separation. The 1 is going to come out and be the coefficient for what's going to happen with x plus y to the 0. X plus y to the 1. The 1, 1 is going to be the coefficients. X plus y squared. The 2. Or the 1, 2, 1 is going to be our coefficients. X cubed. Do you guys notice how the numbers along this diagonal match up with, and if you go back, there's a 0 there, right? The numbers along this diagonal match up with the ends. There are tons of patterns in Pascal, guys. I'm just pulling out a few to help you out. Can you guys continue the pattern? I know some of you have seen it before. What would the next row be?
4.
Because 1 plus 3, if you guys haven't noticed, add the 2 above. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then 1s are always at the beginning of the end. You can think of 1 plus 0, 1 plus 0, if that helps. Just get rid of those little awkward loopy loops. You guys see what I mean as far as this number on this diagonal is going to keep on matching up with the power? Because what would the power be that you're raising x plus y to? The 4th. Could we keep on going? Oh, yeah. But what if I was to ask you something like, and here's where it gets to be a trouble, recursive patterns are cool for building a pattern, but they're not cool for jumping to if I was to ask you for the coefficients of the 9th power. Ugh. What would we have to do to go get the coefficients of the 9th power? And what if I was to say, go to the expansion of the 9th power of x plus y and find me the coefficient of the x to the 7th power term? Oh, that's rough. Now, some of you are like, I got it. It'd be 1 and 5 and 10 and 5 and 1. I apologize. 1 and 5 and 10 and 5 and 1. There we go. No, I can keep on going. I got this. I'll beat her in whatever she's going to teach us. Okay, that's cool and all. But what if I was to ask for the 20th power? Okay, you see what I mean? Pascal's is cool and all. I actually had an extra credit assignment in high school, and I went out to quite a few rows. Maybe I'll show it to you guys on Monday.
I wonder what quite a few
I'm not
rows
entirely
is.
sure if I got them all right, because to be frank, at the end I was just tired of it. But you could expand Pascal's quite far. But do we want to do a huge Pascal's if they ask us for the 20th power on a test and 1 problem out of 20? No. So, there has to be a better way, and there is. Yay! Hey look, it's Pascal. That's fun. But hold on. Are the numbers enough to give the answers? And the answer is no. What else do you have to actually do the binomial expansion? The variables. But once again, are there patterns to the variables as to x counting down from the highest and y counting up from the lowest? Yes, there are patterns. But once again, we don't want to go to the 20th row if we can avoid it. Let's start doing some examples and see if some of them Pascal's is good for and some of them Pascal's maybe is not the best idea. Right, the expansion of the expression. Just FOIL 3 times, I suppose, but that's no fun. What's another way? Pascal's, okay. If it's the 3rd power, kiddos, what row am I going to use to help me out? Wait, why am I using this one? Remember, the second number, doesn't it match up with the number we're raising it to? Cool, so I'm using the 1, 3, 3, 1. Can you guys fill in what's going to happen? That's from Pascal's. What's going to happen with my variables? This one is going to go down, this one's going to go up. So this one's going to start at the max, maximize going to the min, and this one's going to start from the min and going to the max. What do I mean? X starts to what power? Then x is going to count down, x is going to count down, and x is going to be gone in the last term, right? What's going to happen with the 1? He starts by being gone, and then he starts to appear to the 1st power, to the 2nd power, and then finally to the 3rd power. Now, is it hard when it's a 1? No. Because all of them are just 1. So you end up with x cubed plus 3x squared plus 3x plus 1. Dun, 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 dun. Questions. If you can't get this one, the next one's going to be even harder. Where did I get 1, 3, 3, 1? Pascal's triangle. Is there another way I could have gotten 1, 3, 3, 1? Yep, I could have said 3rd power when 1 is to the 0. Raised to the 3rd power. X plus 1 is raised to the 3rd power when 1 is to the 1st power. Raised to the 3rd power when 1 is to the 2nd power. Raised to the 3rd power when 1 is to the 3rd power. This would get me each of my little coefficients. Oops, undo. Ooh, and technically, do you guys notice I actually wrote that last term wrong? That was almost right. I showed you Pascal's and I decided to use Pascal's just because they happen to be the same. Technically, there should have been a 1 cubed after that. So I apologize for that. Are we sure? We're okay? Okay. So, what about this guy? Question. Who's my first? My first term in my binomial.
3.
Who's my second? You guys get negative 4b. Remember, you have a first term plus a second term. So 3a is what is going to go max to min, and negative 4b is what is going to go min to max. Is that okay? Okay. Are we going to do Pascal's again? We're going to be cool like that?
Yeah.
What's the 5 row going to be?
1, 5, 10, 10, 5, 1. Okay. Who's going to go with the 1? Who starts high? 3,
Yep, he starts high. High to low. He's going to be to what power? The 5th. And the negative 4b isn't there yet, right? Okay. What's going to happen to the 3a in the next term? You guys want to finish a term before moving on, or just go do all the 3a's first? Finish a term. So then 3a is going to be to the 4th power, but now who's appearing? Who's building up? Negative 4b to the 1st. Now 3a is going to keep going down, and negative 4b is going to count up. 3a is going to go down yet again. Negative 4b is going to count up again. 3a is going to count down again. Negative 4b is going to count up again. And if you've done it right, the very final term should have negative 4b at the max, which is at n or at 5. And once again, just to quickly make sure we're kind of tracking. That 1 from Pascal's triangle could have been gotten from 5C0. 5 could have, just the 5 could have been gotten from 5C1. Just the 10 could have been gotten from 5C2, etc. 5C3, etc. 5C4, etc. 5C5. But my question to you is, when you finally simplify this expression, are the coefficients going to be 1, 5, 10, 10, 5, 1? Why not? Don't you have these extra numbers going on in your terms? So then, for instance, for this very first term, if we're going to expand him, what's 3 to the 5th power?
243.
Yeah, 243, good. Why am I going to put a minus next? I have a negative next to the first power, right? Now I'm going to have 3 to the 4th power, which is 81 times 5 times negative 4. Which is going to be negative 20. 81 times negative 20.
1620.
A is to what power? B is to what power? Does that make sense? So we have to go ahead and say, hey, 3, you need the 4th power, negative 4, you need the 1st power, and then 5, oh yeah, you're chilling too. We gotta get them all together, working in tandem. We keep moving on. 3 cubed is gonna be 9. No, 27. Ooh, that's rough. 3 cubed is gonna be 27. 4 squared is gonna be 16. It's a positive because a negative squared is a positive. And then times 10. What'd you get, Luke?
4320.
A is now cubed and B is squared. You okay? Keep going along the line. 3 squared is now 9, negative 4. Ooh, that's going to be a minus, good, because it's an odd power of that negative. 4 cubed is 64. 64 times 9 times 10?
57.
67, 60.
No, 57, 60.
A is going to be square, B is going to be cube. So my variables are still counting down, counting up, depending on whether it's supposed to be counting down, counting up. It's going to be a plus because now I have an even power of that negative. 5 times 3 is 15. 15 times negative 4 to the 4th. What did we get?
3,840.
Is anybody checking the car? Or are we just going for it?
I trust it. I told you. Make those mistakes all the time.
Minus 4 to the power of 5. Know that.
Minus Luke.
Wait a minute. Oh no, what else do we need in that one? Stink. There we go. Whew! That ended up a little bit more complicated, but question, did the pattern remain? And was the 1, 5, 10, 10, 5, 1 still important? Yes. But did it determine the final answer? No. Now, after a problem like that, you're like, whew, we're bound to be done. Let's get out of here. But we still have 8 minutes, and we're not done yet. Sorry, it just disappeared. But one more thing before we move on to the next example. Question, kiddos. What if I wanted you to jump to a particular term? Okay? What if I said, you know what? Now, I know we're working backwards. You have the full answer right here. But what if I said I wanted you to find the a to the power of 3 term? So let's say I gave you this initial problem right here. Let me do a new color just so we can separate it. Hey, for St. Patrick's Day. Go get a shamrock shake. Okay, so let's say you had that, and let's say I gave you this. Would you have to literally do all that work and then look at the whole thing and say, so wait a minute, who is he? Oh, there he is. Dun, 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 dun. Or is there a shorter way? Can we see a pattern about what's given in the very beginning, what they're asking for, and how we could maybe jump to just this term? Where did that term come from up above? This one, right? How could we have figured this out without doing that whole expansion? Yeah, yeah. We know that this guy goes here, right? Let's do a new color. Let's use like yellow. I know this guy goes here. I would know that this guy is 3 from that. How would I know the 2 to put in the 5, choose 2? Have you guys noticed what the powers of each of the terms always have to add up to?
5.
Oops, I'm using not a highlighter. That's 5. This is 4 and 1 makes 5. This is 3 and 2 makes 5. 2 and 3 makes 5. 1 and 4 makes 5. I know there's something there, but it's a 1. That makes 5. So if I know that A has to be cubed, what do I know about what's going on with B?
2.
If I know cubed, I know then squared, and if I know squared, then I know 2. Now, do you see how that's kind of a complicated process? But doesn't it sound nice to be able to have a problem and skip straight to the answer using, well, a formula instead of having to do this whole problem and then go looking for the right answer? Let's see if we can do it. Do we want to go to the 9th power, the 9th, technically the 10th row in Pascal's triangle? 1, 9, We could do Pascal's, or we could say, can we figure this out without doing all of Pascal's triangle and then having to plug it all in and then go looking for the 8th term? Screen is already saying, well, we know kind of how this ends up working, right? In the sense of, this is going to be my first term. This is going to be my second term. This is my power. This gets confusing. Because question, what do we call 9, or what have we called 9 up until this point? Isn't he n? So what's with this? Well, they're trying to bring in another n. Well, that's not very nice. So I want you guys to maybe, instead of thinking about n equaling, just think about the 8th term. Just stop there. Just let your brain just think of the 8th term. If you were to expand this whole thing, count 8 over, that's the one they want. N does equal 9. It is raised to the 9th power in the binomial theorem, but how do we get there? How do we jump there? Okay, if we're at the 8th term, we know that we have somebody, well, we know it's 9. Choose somebody. We have to figure out what number to put below the 9 in order to do our NCR and not have to do Pascal's that far. We know that we're going to have 4x raised to somebody, and we know we're going to have 3y raised to somebody. Does the 8th term mean x to the 8th power? No, because you count over 8 spots. X starts at what power? 9. If you're going to count over 8 spots, how many terms are there total? Did we figure this out?
There's
One more than the terms. If you're squaring it, there are 3 terms. If you're doing first power, there are 2 terms. So there's 10 terms total, so we're 2 away from the end. What power has x gotten to? The very last term, the 10th term, x would be gone. The 9th term, x would be to the first power. The 8th term, x would be squared. Now, if x is squared, can you figure out what the y term is going to be raised to?
7.
Good. 2 plus what is 9? 7. Hey, did you guys notice that he's the one that fills in this guy? Why is this so cool? We didn't have to do Pascal's to the 10th row. We didn't have to do the entire expansion and go count over 10 or 8 terms. Instead, all we got to do is do one really cool 9 factorial over 9 minus 7 is 2 factorial, 7 factorial, times 16x squared times, let's just say 3 to the 7th, y to the 7th. We can plug and chug that into our calculator fairly quickly. You can even use your NCR if you're going to your calculator anyway.
That part is 1. No, I'm wrong.
9 to 7 is 36, right? Yeah. Times 16 times 3 to the power of 7. Woo! Ready? Double check me. 1, 2, 5, 9, 7, 1, 2, x squared, y to the 7. Dun, 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 dun.
In this deep, we trust, and that's 8.
You double check me again.
That's enough.
Woo! But do you see the work that saved us?
Yeah.
We would have had to go all the way down in Pascal's. Then we would have had to expand by plugging everything in. Then we would have had to count over the 8th term. So if we can figure out the pattern in binomial theorem, our life would be so much better. Kiddos, we did awesome. There was one that we didn't get to. But you know what? We actually kind of talked about what to do if they give us these powers, right? We'll see how you guys do. Homework is due on Monday. There it is if you want to take a quick picture and not have to look it up later. And I will stop talking. You guys can enjoy the next 30 seconds of silence.
It's all your discretion.
Remember last time we had lots of formulas?
Oh, you already did?
Didn't you have a formula quiz in there? Let's just say keep your notes close. Don't be trying to do things from memory in your homework, and let's try to get good at homework. Bye, guys. See you later, doggy.
Now I have
Been a wild crocodile.
You're like